In the last section, we looked at some examples of constraint systems, and we also looked at the classification of constraints. Now, in this section, we are going to introduce the notion of configuration space and generalized coordinates. This use of configuration space and generalized coordinates is a new way in which we will represent our motion, which we will be using in Lagrangian mechanics. Okay. Now, consider a mechanical system with n particles whose position vectors are given by r1 vector up to rn vector, and the corresponding coordinates are given by x1, y1, z1, and similarly all the way up to xn, yn, and zn. Okay. So, there are 3 n coordinates, and I will denote small n, which is 3 n, and this is in fact number of degrees of freedom of this system. Now, what we are going to do is this: we are going to shade this vector notation, and we are going to stick to only coordinate form. This facilitates again in the Lagrangian mechanics. Now, it would be useful if I instead of using x1, y1, z1 kind of notation, if I use the same letter for all coordinates, that would be of course nicer, and the equation of motion becomes very compact. So, I am going to relabel or redefine new labels as u1 as x1, u2 as y1, u3 as z1, and then u4 is your x2 and so on. So, finally, your un becomes z of capital N. So, z coordinate of the last particle. So, there are 3 n coordinates which I will put it in the n tuplet as u1 to un. Okay. So, the relabeling of the coordinates as u1 to un represents all the locations of all the particles, basically gives you all the coordinates of the all the particles. Now, by the word configuration, what I really mean is if I know the location of each one of those particles, then of course I know the configuration of the system. Okay. And the entire information of this configuration is in fact included in this n tuplet there. So, instead of thinking of the motion of n particles in 3 dimensions, now I am going to think of a small n dimensional space, that is basically 3 n dimensional space. So, I will define a 3 n dimensional space written as R n. This is basically collection of all these n tuplets. So, where each u I is basically a real number. Now, we have a physical world which is 3 dimensional, and now I have this n dimensional space which is abstract space, and this space we are going to call it as configuration space. So, this is a configuration space of the entire mechanical system. And now look at it this way: a single point in this n dimensional space actually represents a configuration of the system. That means a single point there has the information about all the particles or locations of all the particles in your physical world. And as these particles move in the physical world, they would be tracing out their own trajectories. The point in the configuration space also move and it will trace out one single trajectory. Okay. So, a trajectory in configuration space which is given by n functions of the coordinates u1 as a function of t, u2 as a function of t and so on un as a function of t. So, this is the motion of point in the configuration space, and this in fact tells you about all the individual trajectories of all the particles in the real world. Now, we should not be confusing between the two words trajectories. We have individual trajectories of all the particles in the real world, and also we have a trajectory of the entire system. So, remember we will be often using a nomenclature like this: a trajectory of the system in configuration space and as opposed to there are of course trajectories of particles, but these trajectories are in real world. So, in physical space. Okay. Now, what I am going to do is the trajectory of the system, very commonly you will find in many books, is also called as C trajectory, or it is also called as path, both in configuration space. So, let us look at an example. So, if I have a system with just one single particle, it is moving in 3 dimensions, its degrees of freedom are 3, there are 3 coordinates required. Now, what is the configuration space for this? Oh, the physical world itself is the configuration space for this particle, because there are only 3 coordinates there. So, the minimum challenging example would be 2 particles, but you see the configuration space now is 6 dimensional, and then I cannot actually visualize this in our 3 dimensional world. So, what I am going to do is I will do one simple example with 2 particles, but both of them are confined to a physical world which is 1 dimensional. So, both of them are moving along a real line, and here is the configuration. So, now in this example I have these 2 particles. There is a blue particle whose coordinate is say x1 and a red one whose coordinate is x2. And of course, in our nomenclature I will call this as u1 and call this as u2, and they both are in 1 dimensional physical world. So, they both are allowed to move along this line here. Now, what is the configuration space here? Oh, that is going to be 2 dimensional, because now we have a pair of coordinates u1 and u2, and such pairs will form a configuration space. So, configuration space now is 2 dimensional. So, we have configuration space shown here on the left side. In this configuration space, on the horizontal axis we will plot u1 and on the vertical axis we will plot u2. And every point u1, u2 that you are seeing here at this moment are basically coordinates. So, it is a point in 2 dimensional space, but what it actually means is that the blue ball is at location u1 and the red ball is at location u2. Okay. And as these particles move in the space, the dot or the point in the configuration space also moves. So, if you move these points, then the configuration point also moves, and if there is a motion, as you can see here, then of course, the point in the configuration space will trace out a trajectory. So, this here is our C trajectory, or if there is no confusion, I would simply call it as trajectory in configuration space or a path in configuration space. Okay. And individual particles, as they move on the one dimensional plane here, they of course would have their individual trajectories. Now, here the motion does not necessarily mean the equation of the curve in the configuration space. What we mean is this. Let me take one example. Suppose in this example, the particles travel from u1, u2 equal to 0, 0 to 1, 1, and the motion is given by u1 of t is equal to u2 of t, which is equal to t. So, this is a uniform motion. Both the particles are together and they are travelling along the line with uniform speed. Now, the equation of the curve that will be traced in the configuration space is actually simply, so I will call that as equation of curve and not by trajectory, that is u1 is equal to u2. Okay. And here is another possible trajectory, where u1 of t is equal to u2 of t is equal to t square. Or in this case also, both the particles remain together, they travel from 0, 0 to 1, 1 at t is equal to 1, but you see this motion and this motion, even though they have same equation of curve or they travel along the same curve in the configuration space, their motions are different. In first case, the two particles travelled with uniform speed. In the other case, they start slowly and they pick up speed as they run towards 1, 1. Okay. That is because the time dependence here is t square instead of t as in the first example. So, we will make this distinction between the two cases. The equation of curve in configuration space is not the trajectory of the particle. Trajectory necessarily has a time element in it. Okay. Now, there is a related idea, and which of course we will use later when we go to the Hamiltonian formulation, and this idea is what is called as a state space. So, what we have seen here is this. It is not just the locations of the particles, but the speed with which they are travelling in the or the location of the point in the configuration space, but speed with which it is travelling in the configuration space also matters. So, now consider a 2n dimensional space, and I will call this as R 2n, and this 2n dimensional space actually contains all the coordinates and also all the velocities u1 dot, u2 dot and u1 dot. Okay. So, all such ui's and ui dot. So, this 2n dimensional space is called as state space. Look, a curve in state space actually gives you a motion. Different curves in state space means different motion, because now the time element is already built into the state, and we already knew that the Newtonian equations were second order differential equations, and that means if I give you a position and the velocity of each one of these particles, the trajectory is predetermined according to the Newton's laws. So, now here these 2n coordinates, which include position and velocities, is actually called as state of the system. As opposed to configuration of the system. And why does not it depend, why can't we extend this to x double dot? Say in the Newtonian mechanics, the accelerations are not free variables. The forces in the system, they actually predetermine x double dot. So, there is no freedom in choosing x double dot. So, state space here is actually just 2n dimensional, including positions and the velocities. So, now here even in this notion of configuration space, what we have done is this. I have just taken the Cartesian coordinates and relabeled them by new single scheme, okay, u1, u2 up to un, and plotted them as a point in n dimensional space. But all these coordinates in configuration space, they actually refer to the coordinates of individual particles. Now, when we are dealing with one particle, say in a particle moving in a plane, typically if I use Cartesian coordinates and denote them by x and y, it is very common for us to make a change of variable to plane polar coordinates, which is r and theta. Okay? And when we make these coordinate transformation from x y to r theta, then we of course have to rewrite the equations of motions. Now, the first set x y and second set r theta both still refer to coordinates of the particle. Now, look at it this way. If I have a configuration space, in the configuration space, like in the previous example, my configuration space was 2 dimensional. One coordinate was u1, the other coordinate was u2. If I make a change of coordinates in configuration space, see now what will happen. Now, the coordinates of the individual particles will get mixed, and the resulting new coordinates, they may not be referring to the coordinates of any individual particle. Now, this notion is called as using generalized coordinates. So, in the next section, I will describe the use of generalized coordinates. Now, in the previous example, where we had two particles which were moving along a straight line, and the coordinate of one of the particle was called u1, coordinate of the other particle was called u2, and then you have a configuration space, and configuration space is 2 dimensional with one coordinate is u1, the other coordinate is u2. Now, this is just a 2 dimensional plane with two axes, one marked as u1, the other marked as u2. Why can't I make a change of coordinate here? For example, I can change the coordinate axis to something like this. And call this as axis q1 and call this as axis q2. And the transformation between, this is of course a linear transformation from u1 u2 to q1 q2. Now, q1 can be written as u1 plus u2 by 2, and I will write q2 as u2 minus u1. Now, see, the two new coordinates q1 q2, do they give me the configuration of the system? Oh, of course, yes, because I can take these two new coordinates q1 and q2 and I uniquely get u1 u2, or the inverse transformations we can immediately write as u1, which is equal to q1 minus q2 by 2, and u2 is q1 plus q2 by 2. So, given q1 q2, I get unique u1 u2, and u1 u2 is nothing but the configuration of the system. So, I am allowed to do such a coordinate transformation. But look at these two coordinates, this q1 and q2. Now, q1 and q2 do not refer to the coordinate of any of these particles, but of course, we can interpret them. What is q1? q1 actually gives me the center of mass. Of course, I am assuming that the two masses are equal, the center of mass of the system, and q2 here gives me the separation between second ball or u2 and u1. So, these new coordinates q1 q2, they do not refer to the actual coordinates of the particles, but of course, they contain the entire information. This set q1 q2 are called as generalized coordinates. Of the system. And then there is no really end to what kind of transformations you can do. Your transformations need not be linear transformations, you can do non-linear transformations. For example, I can write S1 as u1 square plus u2 square to the power half, or I can write and I will write S2 as tan inverse of u2 by u1. And what would be meaning of S1 and S2? Well, that would be slightly harder to interpret, but thing to remember is even these two coordinates, they contain the information about the configuration of the system. So, in the configuration space, you could use any set of coordinates, and those coordinates will not necessarily refer to the actual coordinates of the particle, and such coordinates are called as generalized coordinates of the system. Okay. I will give you one more example. So, in another example, and this we do very commonly. So, in this case, in the physical world, I have two particles. For simplicity, we will take masses to be equal. So, both masses are equal to m1, and the coordinates of this one particle are given by x1 and y1. The coordinates of the second particle are given by x2, y2, and one set of coordinates. So, basically both particles move in 2 dimensions, each one of them have 2 degrees of freedom. So, the system of 2 particles have 4 degrees of freedom. So, degrees of freedom are 4. So, your configuration space is also 4 dimensional. Of course, I will not be able to show you the 4 dimensional space on the paper, but that is okay. Now, which coordinates we will use? It is very common to use coordinates instead of x1, x2, y1, y2. We can of course use, and this is a very common choice, is to use coordinates like x center of mass, y center of mass, and r and theta. Now, I will describe these. So, the center of mass here will lie somewhere in between, halfway through between m1 and m2. This center of mass has 2 coordinates, x cm and y cm. The coordinate r is basically separation or the distance between the 2 masses. And what is the angle theta? Theta can be chosen to be the angle that the separation vector, angle between separation vector and x axis. And this, of course, you see neither of these 4 coordinates, x center of mass, y center of mass, r or theta, they actually refer to coordinates of any individual particles. All the coordinates are not just linearly, but non-linearly involved in these 4 coordinates there. So, what we actually have here is some sort of a coordinate transformation which relates these 2 sets, and this is of course the most common and most popular choice of generalized coordinates for this problem, and it will also become very clear why we have this, why we choose these coordinates. So, let me make this formal. Okay. So, start by saying that you have a configuration space of a system which is n dimensional and the coordinates are given by u1 to un. So, this is one set of coordinates, and we can now make a transformation to another set of coordinates which I will call as q1. So, second set q1 to qn, and of course, the coordinate transformations are given by. So, for each I, qi must be some function of u1 to un and also probably t. I will add that. This will become clear later, or if you recall, many times we go to accelerated frames, common example being rotating frames, in which case the new coordinates actually explicitly depend on time. So, each coordinate qi must be some function of the coordinates u1 to un and time t. So, this is for all I. Okay. Now, any arbitrary transformation of course will not work. The conditions for the transformation to be a valid transformation are 1. The transformation, so the mappings By mapping, I mean this is 1 to 1 and also invertible. So that unique point, a point is specified by unique set of generalized coordinates. Also, we will insist that the mappings or the transformation functions are sufficiently differentiable. That is, they are smooth functions. They are smooth functions. And finally, that the Jacobian which is defined as J, which is equal to determinant of matrix formed by del Fi del Uj, this must be non-zero. Now, this is of course actually a necessary condition for the first condition there. Okay. And in that case, we say we have transformed the coordinates to generalized coordinates q1 to q1. And now, this of course, even though this transformation gives you new set of coordinates which probably are useful in solving problems, but it still does not introduce any new ideas yet. You just had a n dimensional configuration space which had Cartesian coordinates to begin with, and you made a transformation, or we made a transformation to new set of coordinates. But when there are constraints in the system, then of course something new happens. Constraint means now the point in the configuration space cannot go everywhere in the configuration space. Its motion is now restricted to some region or subregion of the entire configuration space. This is the idea that we will see in the next section. Okay. Now, what we want to do is this. We are going to consider constraint systems and then look at how the configuration space looks like in the constraint systems. You see, in constraint systems, the particles or their motion is restricted in some way. Now, that also means that the point in the configuration space will not be able to go everywhere, but the motion of that point is also restricted in some way. And in this particular section, I will only focus on holonomic constraints. The holonomic constraints, remember, they come in a nice equality. So, if we have a system with n particles with configuration space which is 3n dimensional, or the later we have been using is small n. Now, what we have in the form of constraint is an equation which is a function of the coordinates and probably time t, and this is what we call a holonomic constraint. Now, what is the effect of holonomic constraint on the motion of the point in configuration space is what we want to see. I will start with just one particle first. So, in the first example, consider a particle which is constrained to move on a spherical surface. So, in 3 dimensions, the constraint equation for a particle whose coordinates are given by x, y, z, the constraint equation is x square plus y square plus z square is equal to some r square. Now, each holonomic constraint like this gives you a surface in 3 dimensions. And when I say surface, what we really mean is a 2-dimensional surface in 3-dimensional space. And when we say 2-dimensional space, what we really mean is this. So, in this case too, the surface here is actually not like a plane, but it is a curved surface, and its dimensionality is 2. By that what we mean is this: if you take a point and its neighborhood and approximate it by a plane surface, then it is 2-dimensional, which means imagine a situation like we are on the earth, we are constrained to move on the surface of the earth, but in our local domain it seems like we are only moving on a plane surface. So, in the neighborhood of each point, or the neighborhood of each point can be approximated by a 2-dimensional plane. That is why we call this surface as 2-dimensional surface. In the mathematical term, this is called as a manifold, but we are not going there yet. Okay? That is a subject of differential calculus, but we do not want to employ that language in this course. So, here the particle will be confined to move on a surface of the sphere. Now, all that we know is that on the surface of the sphere, each point can be categorized or specified by 2 coordinates. You can use coordinates like x and y, but there is a little bit of a problem there, because once you give x and y, can you uniquely determine z? Or in this case actually you cannot, because z will be either plus or minus square root of r square minus x square minus y square. So, we cannot determine z uniquely. Which coordinate system? Of course, all of us know that it is going to be spherical coordinate system. In spherical coordinate system, r theta phi, now the same constraint, this constraint here will actually look like r is equal to capital R, and that means the points on the surface of the sphere can be uniquely specified by 2 coordinates theta and phi. And does this theta phi contain the information about the configuration of the system? Of course, it does, because we already know that if I know theta and phi, I can get x as r cos phi sin theta. Similarly, y is r sin phi sin theta, and z is r cos theta. So, all that you really need, because we had one holonomic constraint, the motion of the point in the configuration space is restricted now to a 2-dimensional surface. And on 2-dimensional surface, I need to find one coordinate system which uniquely determines each point, and in this case that turns out to be theta and phi. So, one holonomic constraint reduces 1 degree of freedom, and which also means the number of coordinates required, number of generalized coordinates required to specify the configuration of the system is also reduced by 1. So, in this case the original degrees of freedom without constraints were 3, then degrees of freedom with constraint is 2, and of course, number of generalized coordinates is also equal to 2. Now, what I am going to do is this: I am going to add one more constraint to this problem. So, if I add one more constraint, so in addition to the existing constraint, so the first constraint was x square plus y square plus z square is equal to r square. Let us add one more constraint to this. Say x plus y plus z is equal to 0. Now, what does the second constraint do? If there was no first constraint, the second constraint also gives you a plane surface. In this case, of course, it is a plane passing through the origin. And if I did not have first constraint, I just have the second constraint, the particle will be confined to move on the surface of the plane. How many coordinates are required? Or in this case, of course, you need just 2 coordinates, because given x and y, I can actually uniquely determine the z coordinate. Okay. But anyway, in this case x y suffices. In the first case, we needed theta and phi, but what if the system is constrained by both these constraints simultaneously? Then of course, the particle is forced to move on an intersection of the plane and the sphere. So, the first constraint defines a surface of a sphere, the second constraint defines a plane, the intersection of these two will be a circle. So, circular path is intersection of the sphere and the plane. And now the particle will be confined to move on this line, which is circular. So, what has happened? Now, your accessible region in the configuration space is just one dimensional. Again, why would I call it one dimensional? Because all I need, or if you look at a neighborhood of a point, then it can be approximated by a line segment. So, the number of degrees of freedom now, originally it was 3, but degrees of freedom with constraints is now just 1, which is actually 3 minus. So, original degrees of freedom minus the number of holonomic constraints in the system. And this is the idea that we will take over to arbitrary configuration spaces. So, if you have n dimensional configuration space and if you have one holonomic constraint, this holonomic constraint will define a hypersurface in n dimensional space, and the dimensionality of that hypersurface will be n minus 1. Now, you have one more constraint which is also holonomic, that defines another n minus 1 dimensional surface, and the intersection of these two will be a n minus 2 dimensional surface. So, when we use the word surface, we actually mean hypersurface in the higher dimensions, not just the ordinary 2 dimensional surface. Okay. So, what I will do is I will take several examples from this point onwards. In fact, if I want to show you a configuration space, then of course, I should stay with just 1 degree of freedom or 2 degrees of freedom or 3 degrees of freedom, which I can actually draw and show it to you. But with these examples, we will be able to visualize the abstract n dimensional spaces and the hypersurfaces in those. So, here is my first example. So, simple pendulum. This is a pendulum with length L. The bob is connected to the suspension point by a rigid wire. So, here the original degrees of freedom without constraint are 2 and the coordinates used are x and y. Number of holonomic constraints is 1, and that is given by x square plus y square is equal to L square. Then the dimensionality of the accessible region in the configuration space is 1. So, degrees of freedom with constraint is just 1. So, the coordinate that we will use is in fact the generalized coordinate that we will use here is theta, and that is x is r cos theta and y is equal to r sin theta. Now, the question that we ask is this. So, here of course, it is one particle moving in 2 dimensions. The configuration space without constraint is just the plane xy plane. Once you put the constraint, now the particle cannot visit every point of the configuration space, it has to stay on the circle. But then the question we would ask is this: the manifold or the accessible surface here is one dimensional, but it is not like a straight line, but it is like a circle. So, here another consideration that goes into the accessible configuration space is that the geometry is like a circle. Let me take another example. This is our Atwood's machine, which we discussed earlier. So, there is a pulley which is suspended and there is a mass 1 and there is a second mass here. And the coordinates that we will use is y 1 and y 2 for this, and here of course there is one constraint. So, there is one holonomic constraint which is y 1 plus y 2 is equal to constant, which means our configuration space is actually now one dimensional. Originally it was 2 dimensional with 2 coordinates y 1 and y 2, but now it is 1 dimensional and I can either use y 1 or y 2. But notice that the geometry of, if I use y 1, then the coordinate y 1 varies between 0 and some maximum length L, and the geometry of this one is that of a line segment. The third example is a double pendulum. Here we have one pendulum and the second pendulum is connected to the first one. So, let us say this length is L 1, this length is L 2 and this angle here is theta 1, this angle here is theta 2. The number of, there are 2 masses moving in 2 dimensions. Without constraint, the configuration space would have been 4 dimensional. With constraint, now the number of degrees of freedom are just 2, because there are 2 holonomic constraints here. One is the length of the first pendulum is L 1 and the length of the second pendulum is L 2. So, the coordinates which we will use, are theta 1 and theta 2, and we can of course get all the coordinates of the particles from theta 1. So, x would be sin theta 1, y 1 would be equal to L 1 cos theta 1 and x 2 is x 1 plus L 2 sin theta 2 and y 2 is equal to y1 plus L2 cos theta 2. But then the question we want to ask is this: what is the geometry of the accessible surface in the configuration space? So, theta 1 variable here goes from 0 to 2 pi, and theta 2 also goes from 0 to 2 pi. Okay. I could of course plot these in 2-dimensional plane. I can plot theta 1 on this axis and theta 2 on this axis, and the accessible region here is between 0 and 2 pi for theta 1 variable and 0 and 2 pi for theta 2 variable. Okay. This is the accessible region of the configuration space. But you see, the geometry is like this. In this case, theta is equal to 0 and or theta 1 is equal to 0 and theta 1 is equal to 2 pi. These 2 points are not different from each other. So, the entire line here and this line here of the configuration space are same. So, what I am going to do is in fact fold this plane region and join theta 1 is equal to 0 line to theta 1 is equal to 2 pi line. What does that make? That makes it into a cylinder. And then we realize the same thing is true for theta 2 also. So, what I need to do is take this cylinder and the lower circle of the cylinder must match with the upper. So, you fold the entire cylinder to make it into a torus. So, the geometry of this system with the constraint is like a torus, and this makes it lot more interesting. Now, the geometry here is, remember, this torus is actually embedded in the 4-dimensional configuration space for this system. The 4-dimensional configuration space was unconstrained system. Once we put the constraint, now the point which represents the system can only travel on this torus here. So, the geometry is that of a torus. I will take one more example and then we will complete this section here. In the third example, of a dumbbell. So, you have a dumbbell with 2 masses. The separation between them is given by variable r, and the angle this dumbbell makes with horizontal axis is given by theta. And this, of course, the dumbbell is free to move in your physical 2-dimensional world whose coordinates are marked as x and y. Now, there is one constraint in the system, that is the separation between the 2 masses is constant. So, the constraint here is r is equal to constant. Okay. Let us mark this as d. And remember the generalized coordinates for unconstrained system. We considered this dumbbell example earlier, and the generalized coordinates which were most common were y center of mass, r and theta. This was for unconstrained system, but now I have one constraint which is r is equal to constant. That means the accessible space here is xcm, ycm and theta. And I can of course plot this in 3-dimensional space, where I will use, so the configuration space here will look like this. I can plot x on one axis, y on the other axis, and then theta I can plot on the third axis. But remember, theta takes values only from 0 to 2 pi. And what must happen here? Theta is equal to 0 plane, which is xy plane, is also same as the theta is equal to 2 pi plane. And somehow I must sort of fold this together to join theta is equal to 0 plane and theta is equal to 2 pi plane. Of course, in 3-dimensional pictures here, I will not be able to show you that, but what will it really make? It makes some kind of a hypercylinder in 4-dimensional space. Okay. However, for the purpose of depiction, I could actually stay with simple diagram like this in 3 dimensions itself. And remember, every time I am tracing out the trajectory of the system, as the dumbbell rotates, the trajectory moves upward in the theta direction, and when it completes one rotation by 2 pi, it actually exits from here and jumps back into the theta is equal to 0 plane. So, this is another way in which we can visualize the configuration space here. So, this sort of summarizes this section. When you have n particles, you have 3n dimensional configuration space, but if there are constraints, if there are k constraints which are holonomic, then each of these constraint can be used to eliminate one of the variables. And so, in the summary, for n particles, with k holonomic constraints, the dimensionality of the accessible configuration space is reduced to 3n minus k. So, with constraints, degrees of freedom reduce to 3n minus k, and somehow we should be able to find 3n minus k generalized coordinates. So, sum q1 to qm, which uniquely determine points on the accessible surface. These are called as generalized coordinates. The same name, generalized coordinates, for constraint system. Okay. So, in the next section, I will now start using the idea that the normal forces in the system, which actually give rise to holonomic constraints, they are perpendicular to the surface, accessible surface of the configuration space, and hence those forces, constraint forces, will not do any work. And then we will take one more step towards the obtaining Lagrange's equation.